I'm in Bristol today, Bristol, UK. The name of the city actually derives from the Anglo-Saxon Brixtow, meaning the place of the bridge. So I would say I'm in the city of bridges. It's 6:30 now and looks like it's going to be a nice sunny day. So why don't we go on a tour of all the bridges in town? And it's no fun walking across the same bridge twice, right? So let's try to cross every bridge here exactly once. Starting with that one, Bristol Bridge. Welcome back to Complexity Papers. This is going to be the third lecture in my Networks and Complexity course. Links to the other lectures are in the description. But now we need to get going, because this one will be quite a trek. The challenge that we are attempting today is a famous historical puzzle. But originally it was not about Bristol, but about Königsberg, the Prussian city that is modern-day Kaliningrad. In 1736, Leonard Euler was challenged to find a route that takes a walker across every bridge in Königsberg exactly once. This is the famous Königsberg Bridge Problem. Back then, and perhaps even today, most people wouldn't have recognized this as a mathematical problem. But Euler knew a math problem when he saw one. So let's take a look at a map. We can see that Königsberg occupies two banks of a river and also two river islands. The city is thus divided into 4 quarters. These quarters are connected by 7 bridges. But here we see a shortcoming of this beautiful map. While it's very nice, all the detail obscures information that we really need. We can hardly see the bridges here. When working on a difficult problem, we want to clear our mind of all the unnecessary bits that clutter up the picture. So we want to work with lean models that only contain the bare necessities for capturing the essence of the problem. In this case, this is the quarters of the city and the bridges. So let's draw a map that shows just that. So our map has become a network in which the links represent bridges and the nodes represent quarters. And it's a quite peculiar network, because some links connect the same pairs of nodes. We call such links multilinks, or we can also say they are parallel edges. And networks which contain such parallel edges are called multigraphs. We can even imagine that a bridge would lead back to the same island it started from. That would create a loop in our network. So networks that contain such loops are called sometimes pseudographs. If you want to say that a network doesn't have loops or multilinks, so it's just an ordinary network, we can also call it a simple graph. But let's get back to the challenge. We want to find a walk that crosses every link exactly once. In honor of Leonard Euler, such walks are called Eulerian walks. And if they take the walker back to the starting point, they are called Eulerian cycles. But how do we actually find such a walk? In this lecture, we are ultimately going to arrive at a problem-solving strategy that we will call trial and error. But you probably already know what trial and error means, right? So why don't you give it a try and find a solution to the Königsberg network? You can have a look at it, but remember, you are only allowed to cross every bridge exactly once. And in the meantime, I will cross some more bridges in the real world. So, have you found a solution? Well, if not, let's go through the problem-solving approaches that we already know. First, we could try a greedy algorithm, right? But how would we even do that? Just start somewhere and then pick bridges at random? That takes us right back to trial and error, doesn't it? So, greedy algorithm is not going to work here. How about branch and bound? Here, this is how this could work. We make a list of all the starting points. That is our initial set of proto-candidate solutions. And now we take one step where we take one of them and expand them by one bridge. Well, there's quite a lot of options here, depending on which place you start from. But yeah, that gives us an even bigger list of proto-candidate solutions, right? So yeah, is this going to work? Yes, eventually it's going to work, right? This is a way to map out all the possible solutions. But the power of branch and bound really comes from being able to bound, from being able to exclude some of these candidate solutions early on. Now, if you think back to your trial and error attempts, I would guess that most of them failed in the final step, right? So if that is the case, and most solutions only fail in the final step, that means that in branch and bound, our candidate solution list will grow for a long time before we can eventually start to bound it back down. And because this is so, branch and bound is not going to work well here, right? This is why trial and error is such a powerful strategy. From doing some trials, we learn so much about the problem. In this case, we learn that branch and bound is probably not a good idea. So we'll have to look for something else. This leaves us with a brute force approach. We know that each successful solution must contain all 7 bridges exactly once. So we can just look at all sequences that contain all the 7 bridges and then check which one of them is walkable. How many sequences do we actually have to check? Well, there are 7 options for the first bridge in the sequence. And once we have picked the first bridge, we have 6 options for the second bridge. And then we have 5 options for the third bridge, and then 4, and then 3, and then 2, and then 1. And of course, we recall options multiply. So the number of sequences is 1 times 2 times 3 times 4 times 5 times 6 times 7. We can write this actually as 7 factorial. This is just a shorthand notation for the product of increasing numbers from 1 to 7. The factorial is an example of a function that rises faster than any exponential. But 7 factorial isn't actually that much. It's just 5040. And half of these 5040 sequences are actually identical to the other half, walked backwards. So this leaves us with 2520. Even in 1736, we could have sat down one morning with a quill and a big scroll of parchment to write out all of the sequences. We probably would have been finished around noon. And then within the span of the afternoon, we could have checked every single sequence, crossing each one out when we found it to be not walkable, at least not without a swim. Today, people seem to believe that the Königsberg Bridge Problem is an actual real problem that people were desperate to solve. But that's not how it was. See, before TV and the internet, people were awfully bored, so they entertained themselves with puzzles. And if you were especially bored, it might seem like a good idea to pose an unsolvable puzzle to your friends. So this is what the Königsberg Bridge Problem is actually all about. It's 18th century people trolling each other. So now we go to the back of the shopping center where they keep the bins, because there's a tunnel under the railway there. But solving the problem by brute force in the 18th century? That should have given you at least some bragging rights, shouldn't it? I mean, you could have grabbed your big scroll of parchment containing all the crossed out sequences and then taken it to the pub, right, to show your friends, to prove once and for all there's no solution to the bridge problem. If your friends wanted to check your brute force solution, there's no way they could do this except going through the whole list again and actually repeating all the work. Leonard Euler was actually aware of the possibility of a brute force solution. Here's what he has to say about it.
When the analysis is undertaken in the manner just described, it yields a great many details that are irrelevant to the problem. Undoubtedly, this is the reason that the method is so onerous. Hence, I discarded it and searched for another more restricted in its scope, namely a method which would show only whether a journey satisfying the prescribed conditions could in the first instance be discovered. Such an approach, I believed, would be much simpler.
Now, this is a powerful idea. Economy of information. If a method extracts less information, it must also be simpler to use. This is actually a very valuable principle that will guide our thinking in many of the upcoming lectures. So, let's ask a simpler question. Instead of asking, how can we possibly do the work, let's ask, how can we possibly fail? Of course, we will definitely fail if the network has links in multiple components. But this is a silly way of failing. So let's ignore it from now on, and let's assume that the network is connected, or at least has only links in one component. From our trial and error attempts, we know that another way of failing is to trap ourselves in a node that we cannot leave again without using a link twice. So let's think about this in a little bit more detail. We have an obvious problem if there's a node that has only one link connected to it. In network science, we say that the number of links that connect to a node is a degree, or more specifically, the number of endpoints of links that are on a node is a degree. So let's consider a node of degree 1. Because there's only a single link, we get a problem, right? Because once we use this link, we are trapped on the island. We could also start at this node and then use a single link to leave. And in that case, all is okay. But in either way, a node of degree 1 must be the start or the end point of an Eulerian walk, if such a walk exists. So what about nodes of degree 2? Here we don't have such a problem, right? We can use one link to arrive at the node and another to leave. But a problem exists if we start in a node of degree 2. Then we use one link to leave, and the next time we arrive at the node, we trap ourselves. So if a node of degree 2 is the start point of an Eulerian walk, it must also be the end point. So what about nodes of degree 3? Clearly we must visit these twice in order to use all the links. On our first visit, we can use one link to arrive and one link to depart. And after that, the node has effectively become a node of degree 1. We need to visit it one more time, but on the second visit, we trap ourselves there. If there's a node of degree 3, it must be the start point or the end point of the Eulerian walk, or no Eulerian walk exists. The same is true for all nodes of odd degree. Consider, for example, a node of degree 15. To use all 15 links, we will have to visit this node 8 times. On our first 7 visits, we use up 14 links, 7 to arrive and 7 to depart. Then on the 8th visit, there's only one link left, so we get stuck in the node. So each node of odd degree can only be the starting point or the end point of an Eulerian walk, if such a walk exists. Because our Eulerian walk can only ever have one start and one end point, there can be at most 2 nodes of odd degree. If there are more than 2 nodes of odd degree, an Eulerian walk cannot exist. So, if a network contains exactly 2 nodes of odd degree, we can choose one of them as our starting point. Then we can do the walk, and if we are successful, we will end up in the other node of odd degree. So how about networks where every node has an even degree? Well, in that case, we can just pick a start point somewhere, do our Eulerian walk, and because we cannot get stuck in nodes of even degree unless they are also the start point, our Eulerian walk will take us back to the start point. So in networks where all nodes have even degree, an Eulerian walk exists, and the walk is a cycle. Let's summarize what we learned. If a network doesn't have any nodes of odd degree, then an Eulerian walk exists, and also the walk is a cycle. When a network has exactly 2 nodes of odd degree, then an Eulerian walk also exists, But it won't be a cycle, and one of the nodes of odd degree will be the starting point, while the other is the end point. Finally, if there are more than 2 nodes of odd degree, there cannot be an Eulerian walk. Unfortunately, this is our next bridge, J. Ferry Bridge, and it's closed for construction. Also, it just started raining. I think in this case, we are allowed to invoke a little bit of YouTube magic to cross it. I will do it like this. I'm on the other side now. That counts, doesn't it? Anyway, let's go on to the next bridge. Let's return to the city of Königsberg. If you look at the map, we can see that 3 of the nodes have degree 3 and 1 has degree 5. So in Königsberg, all nodes have an odd degree. So 4 nodes of odd degree, that means there's no Eulerian walk. Of course, this is no coincidence. If the Königsberg Bridge problem had a simple solution, somebody would have just solved it, and we wouldn't be talking about it today. But there's more to this. If you want to troll your friends, you want a problem that is unsolvable. And you also want it to be looking innocent enough that they waste time trying to do it. I claim this is exactly what the Königsberg Bridge graph is. This is the simplest network that has no solution, and it's not immediately obvious that there is no solution. So this is what the Königsberg Bridge graph is. It is the ideal trolling network. Euler's proof was felt to be so beautiful that it inspired other similar works. And eventually these became graph theory, the mathematical study of networks, and by extension, modern network science. Okay, we've seen a very elegant proof that there's no solution to the Königsberg Bridge problem. But I see that some of you are still dissatisfied. And that's okay. In fact, I've been here before. You know, if you work with interdisciplinary teams, you quickly learn that different disciplines have very different standards for success. If you prove that a problem has no solution, for the mathematician, that is mission accomplished. But the engineer is not happy yet. In fact, if you tell the engineer you want a walk, the engineer will make a walk. If it's not possible with the present bridges, the engineer will build a new bridge or demolish an existing one. But here in Bristol, we are not done yet. There's some more bridges to cross, including a few big ones. So there's more stuff coming up. In fact, you can watch the video right now. But maybe you want to first join me for some exercises and discover some deeper properties of bridges and networks. That sounds tempting, doesn't it? In any case, see you in the next one.